Okay, today we're going to be talking about conversions, empirical formulas, percent composition, and percent yield. It's a lot to cover in one day, but we can do it. Let's look at these examples here. There's several examples done for us. One thing we want to look at when we're converting from one unit to another in chemistry is we first want to look at what we're given and then what we're trying to find. So if you notice in these cases we're given liters and we want to find moles. There's a handy conversion factor which is 22.4 liters in a mole that's used in chemistry, and it's for any gas at standard temperature and pressure. Now there's nothing here that indicates that it's not at standard temperature and pressure, so we can just assume that that would be good. So if you look here, the liters that are given, you would use 22.4 on the bottom so that you can cancel those liters, and then you get moles as your answer. You could see some other examples here. Now in this case, you're given moles, but you're trying to find liters. So you can still use the same conversion factor, but instead of having 22.4 on the bottom so that those liters can cancel like in the previous problems, you would put it on top. You can do that. You can flip that conversion factor whichever way you need it because it's essentially equal. It's the same as saying 12 inches equals 1 foot. And so you can put them in any order you need. In this case, you want to put 1 mole on the bottom, 22.4 on the top, and so your moles cancel. These are all gases, and there's nothing to indicate they're not at standard temperature and pressure, so that's why it makes it so easy to use these conversions this way and use the 22.4. The next section talks about or shows how we can convert from liters to grams. Now there's no conversion that converts from liters directly to grams, but there is a liters to moles, and then you've got moles to grams. And I want to caution you that you pretty much always want to have a conversion that includes moles, no matter what you're doing. If you don't get through moles, chances are you're doing something wrong. So be sure to always look for a way to get to moles if one of the starting or ending units is not a mole. So what we did was we started with our 22.4 liters per mole, like we did last time, but then we moved on to moles and grams. The only way to get from moles to grams is by using the periodic table. What you have to do there is you have to add up all of the elements that are in a compound. Like down here you have nitrogen dioxide, so you would have to add up 1 nitrogen and 2 oxygens from the periodic table in order to have the entire molecular mass of that compound. I would also be careful about nitrogen. Nitrogen is one of your Brinkelhoff elements. Nitrogen is a gas, and as a gas it's going to be N2. It's a diatomic. So that means when you're doing your conversions with nitrogen or oxygen or bromine or iodine or chlorine or hydrogen or oxygen, any of those Brinkelhoff elements, then you want to make sure that you use the diatomic molar mass. Okay? Here we're going to go from grams to liters. So again, you're going from grams to liters, but first you'll need the molecular mass from the periodic table. You would add up 2 fluorines and then go from moles to 22.4 liters since we're a gas. And then you would multiply your numerators, divide by your denominators. Some of the numbers here may not look like the numbers you get on your calculator, and that's because I have rounded to the significant figures that I have been given in the problem. So in this case, there's only 1 sig fig in 1 million. So our answer cannot have more than 1 significant digit in the answer. So that may be some of the differences that you find with your answers. Okay, now we're moving on to particles. Particles should give you a hint that you're going to use Avogadro's number, which is 6.02 times 10 to the 23rd of anything in a mole. Generally, since that's such a large number, you would use that for ions or molecules, those kinds of things that are teeny, teeny, tiny. You wouldn't use them for things like iPads or something like that that's really large. That would be a huge amount. But here, you're going from liters to moles using the 22.4 liter per mole conversion, and then go from moles to particles using Avogadro's number 6.02 times 10 to the 23rd. When you multiply the numerator and divide by the denominator, this is what you would get on the right. Okay? Now we're going to go the other way around. We're starting off with particles, and I abbreviated with part. because there's not really a good abbreviation for particles. So you start with particles of your gas, divide by Avogadro's number, and then multiply by the 22.4 liters per mole. You want to set up your equation every time so that the units that you start with are the units that are going to be canceled. And then you're going to hopefully get moles very quickly. And then moles are canceled. And you're left with the one unit that you're looking for, that they're asking for. So that's sort of your goal. You want to map it out that way. Okay, let's get to something new. Percent composition is, I like to think of it as like a candy bar. What's the percent composition of a Milky Way bar? There's a certain percent that's nougat, a certain percent that's chocolate, and a certain percent that's caramel. And so when you add all those up, you would get 100% because that's the whole candy bar before I have any bites of it. In a percent composition is similar. You take the total mass, it's always by mass, the total mass of your compound. So you would look on the periodic table at lead and sulfur and add those up, and that would be your total mass. Then what you do is you take a ratio of what is the mass that lead contributes to the compound, divided by the total mass, and multiply that times 100 so you can get percent, and that would be the number that you get. So in this case, you're going to have 2 carbons, which would be 24 grams, and 6 hydrogen, which is around 6 grams. So the total grams here is 30. So your carbon is 24 divided by 30, your hydrogen is 6 divided by 30, so you're going to get something like an 80%, 20% split for this next problem. And here are some other helpful examples for you. But percent composition is talking about specifically that compound. Now percent yield is very, very different than percent composition. Percent composition again is just what percent of the mass of each of the type of element in that compound contributes to the total mass. Percent yield, I like to think of, because I always think about food, is I like to think of how much brownie mix actually made it into the brownie pan. And if you're anything like me and you like brownies, when you're making the mix, or maybe you're making chocolate chip cookies, not 100% of that mix goes into the pan. There's a little tasting going on, there's some left on the spoon, there's a little bit left on the bowl. If you're kind of a wild mixer, there might be some on the counter, and so not 100% goes into the pan. Well, when you think of chemical reactions, not 100% of every reactant is going to be converted into the products. The chemical reactions do not happen at 100%. So here's this handy formula, and the handy formula says the percent yield of a reaction is the actual yield, how many grams did you make of your product, divided by what should you have made if the entire reaction went perfectly in an ideal world, and then you multiply that times 100. So in this case, you actually only got 24.8 grams of whatever product you were supposed to get in the reaction, but you should have gotten, if everything worked out perfectly, 25 grams. And so your percent yield is 99.2%. Again, down here, be careful because the actual was listed second. You made 161 grams of something, you should have got 187 grams. Take that fraction, multiply by 100, and so your total percent yield of the reaction was 86.1%. Again, I use the significant digits based on what's given in the problem. Here is another example. Jim only measured 9.5 grams of product, but he should have gotten 16.0 grams. You take that division, multiply it by 100, and you get 59% yield. Okay, here's some more examples. All right. Be careful in these word problems that you don't just look at the numbers and not really read the question, because that can trick you sometimes. They don't actually only give you 2 numbers and then you just take those numbers in a fraction. For example, in this case, if you had not really read the problem and you just took 1.9 and divided by 30, you would get a very, very different answer than what you should have. If you read the question, it says that this person lost 1.9 milliliters of the potion. And so when you're losing or less than, that means you had to subtract it. So our actual yield is 30 minus 1.9, and so you had to calculate the actual yield. That happens oftentimes in these problems. So be careful about just looking at the numbers and not reading the question. especially if they're more creative, kind of fun questions like are written here. This is a Harry Potter fan, I take it, for the person who wrote these questions. Okay, so moving along, sometimes you would need information from the question above. For example, on this one, it talked about he has a volume of 1.37 liters less than it should have. Again, you would have to take 1.75 minus 0.37, you would get 1.38 liters. So his real yield is 1.38 divided by 1.75 times 100. And you end up getting 78.9% for that one. Okay. Now the last thing we're going to look at is empirical formula. And empirical formula is basically what is the simplest possible formula you could get for a compound if you reduced it to its simplest ratio. In other words, H2O2, even though that's a specific compound, technically the simplest form of that would just be H and O. Now this first one's a little hard to start with, so I would like to start with one down here and then go back. But basically there's a compound that has 56.58% of potassium, 8.69 of carbon, and 34.73 oxygen. Now, when they say percents, percents are almost always in mass. You need to think mass. So they don't tell you how much of the compound you have. They don't know if you have a gram, 100 grams, 1,000 grams, 1,000,000 grams. You have no idea. But what makes it easy is if you just assume that you have 100 grams. So you would take 56.58 grams of potassium and then divide it by its molecular mass. And let's look at this real quick. Might be easier to see. But we're basically converting grams to moles and grams to mass. And the reason we're doing that is because when you write an empirical formula, like here, this represents 2 moles of potassium, 1 mole of carbon, 3 moles of oxygen in this compound. Okay, so this is the molar ratio of each of these in a compound. So if you want to think of it this way, I'm going to just take this and kind of move it down here. If you take 56.58 grams of potassium and you converted it to there's 39.098 grams per mole from the periodic table of potassium. Okay, what you're doing here is you're actually converting this to moles of potassium, and then that's the number that needs to go right here. But if you'll notice, when you do these calculations, okay, the first time you do them, you may not get nice, neat numbers like 1 and 2 and 3 and 5. You're going to get some kind of weird looking numbers, like 1.5 is not so weird. 0.72 is looking a little weirder. So basically what you would have put down here is 1.5, 0.72, and oxygen would be 2.17 when you do these 3 calculations. Well, this kind of chemical formula just looks weird. We're just not going to use that. When you use a chemical formula or an empirical formula, you need whole numbers. You got to figure out how to make all these guys a whole number. There's a couple different ways to do that. Usually the first thing you do is divide all of them by the lowest number. Okay. In this case, the lowest number is here. So you divide this by 0.72, divide this by himself by 0.72, and then this guy by 0.72. And when you do that, you end up getting nice round numbers. You get 1 for carbon, you get 2 for potassium, and 3 for oxygen. That's how we came up with the formula. And you normally put it in the same order as what's provided in the problem. But sometimes you do all that and you still don't get a nice round number. You might get 1.5 and 0.5 and 2.5 or something like that. So then when you get that, you might have to double them. Usually that's what I do when I see those 0.5s, because I know that when I double a half, I get a whole. So you would get a 3 and a 1 and a 5. So then you would have those as your subscripts in your equation. So be careful about that, because sometimes that will happen. So if you look down here, there's some other examples that you can look at. Again, we assumed 100 grams of each. We did our division, and then we divided by the lowest. And here's a couple more. The empirical, again, that's the lowest, simplest ratio of each element.